Now we are ready to start the second stage of the final round. The problem which will be reported is problem 1, invent yourself. Please, each team send a representative and write down your name on blackboard. Okay, so we will start. Preparation of the reporter is ready. Are you ready? You still want 5 minutes. Yeah, it's up to you because it's for you to prepare. If you okay, you need 5 minutes. Okay. I'll start the presentation.
Good.
12 minutes. Okay.
Good morning, everyone. We are 44 from KSHS, and today we are going to present the number 1, invent yourself. So here's our overview of the structure. First of all, we'll talk about the problem, then we'll have a view of some paper research, and we are going to see our design and optimization of our SIS device and have some conclusion. So first of all, let's see the problem statement. The problem statement says it is more difficult to bend a paper sheet if it is for accordion style or rolled into a tube. And the problem wants us to use a A4 sheet and a small amount of glue is required and construct a bridge spanning a gap of 280 millimeters. And our goal is to introduce parameters to describe the strength of our bridge and optimize some or all of them. So here's our device. We use force sensor to measure the force, and the force sensor is connected to the computer, so we can get our data immediately. So here's the software we use. As you can see, when we pull the force sensor, the data will go into the computer. So here's our definition of the strength of the bridge. We define the strength as the maximum external force before it collapses. Okay, so let's go into the paper research. First of all, I want to introduce the area moment of inertia, which is different from the moment of inertia. And the area moment of inertia is the parameter to quantify the property of the shape. And as the reference gives us the equation we can use. And here's the second cause of the collapse I want to introduce is the bending moment. So we all know when there's a force exerted on a bridge, and if the bridge doesn't have the acceleration, the total force must be 0. So the force must be divided to two parts, two even parts. And let's take a look at the left part. So, just as I mentioned, force must be 0. The total force must be 0, so there will be a force produced at the right side of the bridge, but that will cause a torque. But we know that the paper bridge is not moving, not rotate, so there must be a moment which is the different direction of the force right part, just like this. So then I'm going to introduce the third cause of the collapse, which is the bending. And here's the equation that the reference gives us, and we'll use at the design part later. Okay, and the fourth I want to introduce the buckling, and also, and the same is given by the reference, which called the mechanics of material. And this equation we can use in our design too. So here's the summary of my paper research. First is the bending, and the maximum force which will affect the maximum force is the force which is perpendicular to the surface of the bridge. And we know that the stress will equal to a moment multiplied by y, which is the distance of every point to the neutral axis over the I, and the I is the second moment of inertia. And we also know that the perpendicular force is proportional to the moment. So we can know that the force is equal to a constant multiplied by I over y. Second is the buckling. So what the main effect of the buckling is the parallel force, and which is equal to a constant multiplied by I over L squared. So let's take a look at our design. So this is our first design, the accordion style. And this is the third picks, 4 picks, 5 picks, and the 6 picks. Okay, so as you can see, the 2 picks is easy to collapse, and the 6 picks is harder to collapse. And in our experiment, we get this graph, and it's quite interesting because it's obvious there has 2 regimes. So first, according to the reference 1 and reference 2, if the parallel F is bigger than the alpha multiplied I over L squared, the collapse is caused by the buckling. And if the perpendicular force is bigger than the a constant multiplied by I, then the collapse is by bending. So the total force will be divided to even parts on every piece. And this is the left part of the graph, and we linearize the graph. As you can see, here is the square of the peaks and the load. So we can know that the load has a linear relationship between the peaks square. And here's our discussion of this. As I mentioned, if the parallel F is bigger than the alpha multiplied by I over L squared, the collapse is by buckling. And we know that the second moment of inertia in this shape is equal to 1 over 12 multiplied the L over 2n multiplied the t cube. And that's the I is proportional to the 1 over the n, and n is the number of the peaks. So that's why the maximum force is proportional to the n squared. And here's the right part of the graph. And as you can see, the force is independent of the peak. And here's our discussion. So if the perpendicular force is bigger than the B multiplied by I, the collapse is by bending. So the I is the same of this shape is I is proportional to 1 over n. So we can know that the maximum force is nothing deal with the force, the peaks. Sorry. And here's the software we use to calculate the second moment of inertia. Okay, and here's another design, the cylinder. So we get that the force and the peaks has a negative relationship. And here's our discussion. We use the software I mentioned to calculate the second moment of inertia. And as you can see, when the diameter is bigger, the area moment of inertia over the radius is bigger too. But that means the force will be bigger, and it didn't match to our experiment. So we try to figure out why. So when the force is exerting on the cylinder will be change the shape to a flat piece of paper. So and we measure the second moment of inertia of this shape, and we get that when the radius is bigger, the inertia will be smaller. So that's why this is fits to our experiment. Okay, so let's do some optimization. So the first type of our design is the accordion style, and the best condition of that is the peaks bigger than the 6 peaks, and then you will have the maximum force of 2.81. And the type of the cylinder, when the radius is equal in our experiment, the radius is equal to 1.2, they will have the maximum force of 4.87. But we think that as small as possible, the radius is the maximum force the cylinder can bear. And here's another shape of our optimization, which is the double cylinder. And it has a force of 5.87, and the 2 layers, 2 peaks has the load of 4.47. So here's our conclusion. The strength of the bridge is closely related to the area moment of inertia, just as I mentioned in the paper research. And the collapse of the bridge is due to either bending or buckling. And of the accordion style, the more peaks, when the peaks is smaller than 6, when the more peaks is, the strength will increase. But when the peaks is over the 6 peaks, the peaks have little influence on the strength. And when the radius of the cylinder is smaller, the strength will increase. And in our optimization, the 2 round 2 circle has the maximum force of 5.87. And that's all for my presentation. Thank you.
Yeah. We will have 2 minutes for the opponents.
And thanks for the reporter for giving such a great presentation. And I clearly have a brief view of and I will ask some questions. So, do you pull the paper bridge by the hand?
Yes, but we do the experiment many times. So I think, and we also do the error bar. So I think the error is in our control.
And have you considered a different degree of the angle when you put on the bridge? It's like, if you put a bridge, it's like this. Do you have considered different angle?
Oh, I make sure the width of the bridge, so the angle of the staircase will be the same.
And can you turn to your page when you mentioned accordion style experiment? And
This one.
no, accordion style. And can you, because I didn't really clear about what parameter have you control in this situation. Is it only the peak in single A4 paper?
Yes.
So is the width controlled?
The width is controlled.
Okay. And have you calculated? Do you know that there's two kind of buckling?
No.
Because like there's two kind of buckling, which is one is a long column buckling, and another one is a short column buckling. And there's a condition which a long column buckling can be used for the play load force, and another one is which you cannot use the formula that you gave. First, you need to know that the cylinder ratio is bigger than the column constant. Have you calculated both ratios?
Okay.
Thank you.
Three minutes for the opponent to prepare.
Skip to the discussion. Sorry, take it slow. And here, thanks to the reporter for giving us such a clear presentation. And here's some reporter's main points. He had mentioned that he had done some paper research, and knowing that why the main effect of why the paper bridge has strength is according to the different area moment of inertia according to different size and different shape of the paper. And the bending moment and bending and buckling, the reporter has given us a very clear explanation how these effects are acting on the paper bridge. And the reporter also confirmed that according to his experiment, there are two regimes that mainly is buckling and bending will affect the maximum flow force that the paper can bear. And consider the radius in the cylinder, he had considered the radius was being increasing and which will lead to an inertia to increase. But actually, he found that he thinks that the paper will be, the shape will change, so which lead to the inertia of the area moments will change, which will decrease the payload of the paper bridge. And I wish to skip to the discussion.
The rest.
And here I want to confirm another question. How can you ensure that the load is separate evenly?
We use the C cardboard
Yes.
to separate the force to every piece.
And in your experiment, video, I see that you use an area to press on the board. What do you think if we use a line or a stick to press on the board? What will affect the payload?
You mean?
Because we can see in your experimental video, it's like when you pull the paper bridge, it's an area, it's a cardboard.
Yes.
And what do you think if it is pulled by a stick? Would it affect your experiment data?
You mean the attaching area?
Yes.
Oh, we have done this in the. Wait a minute. You mean this?
Yes.
Yes, and we have some data, which is a parabolic.
Why it is parabolic? Can you explain to me?
By using the buckling formula, we can know that the F is proportional to the N squared.
Okay, and since that you have said that both the stress, the bending and the buckling have used the second moment of inertia, is it you use the same inertia in your experiment? Is it the same inertia in your experiment?
If the shape is the same, the inertia will be the same.
But I have I need to clarify another thing. So here is the bridge. Yes. Okay. Sorry. Here's your bridge. So when you put a force acting on it, it will bend. Yes. So the second moment of inertia is using the area of this cross section, isn't it?
Yes.
But
what I consider is there will be a bend on this direction.
yes, you bend like this.
Yes, but just look at a single piece.
Yes.
And when the force is exerting on the piece, the shape will change like sort of like this.
Yes.
And if the piece is acting like this, the strength will decrease much.
Yes.
So I think the force of this making the shape of this is bigger than the bending. So the maximum force we consider is this
How can you show it?
of our observation.
So you don't. Okay.
Okay, I also do just put a no force
Yes.
paper sheet on the bridge,
Yes.
and we find that the load on it is very, very, very small.
Okay. And like I have just mentioned, because since there are two equations, like two situations of the buckling, that because it's dependent on the cylinder ratio, well, if the cinder ratio is bigger than the column constant, which the cinder ratio is calculated by the K, which is the anti-fixity condition, and the L, length of the paper out of the radius of gyration.
Excuse me, you mean the end fix?
Yes, because first there are two problems. When you need to use a long column, the end fixed situation needs to be fixed. Then because they are.
But in my experience, the paper doesn't have the end fix.
No. So your condition is that the paper when you press it will move. It's not a pin column. It's like if you put a column like this, if this part cannot move but it can rotate, it's a pin situation. So what is your situation? Is it can this part move or will it move all the way? Because since that the paper is like the friction is not, you're not putting it into a gap, or I think that it will move too. So how can you show the difference between? Have you sure that it is in on the when you
I think the K here will not affect the, because it's a constant.
But it will, because the different condition will change the constant.
But all of this is the peaks, right?
Yes, but in sometimes when you press like if this is a key, when you press, it didn't move, but sometimes the paper down here might move too. Because I think you just control the whole width.
Yes.
You didn't control the width between each piece. I'm right. Because when you are pressing, then you will have some slight change of the displacement, which will lead to the situation. It's not the constant.
But every piece has the almost same situation of the, just like I said, the move of the downward path, right?
Yes.
So if the K here is the fixed, the K will have equal a number, right? But if it is not fixed, it will equal to another number. But in the experiment, the movement of the downward path, I think, is similar.
Okay. And can you explain again can you turn to the optimized part? Can you explain why the peak is over 6?
I have mentioned in my presentation, the graph has two regions, and sorry, wait a minute. Just like this.
Yes. But in the graph, I think that the 7th peak is higher.
I think that is an experiment error, because if the line is linear, the line will go across the error bar. So I think it's an experimental error.
I see your error bar. Okay. So how do you, the line is, I think the line is parallel to, is it parallel to the axle?
I think it is.
Then if there is a million peaks, so
Yes.
it will still be.
If there's a million peaks, you can assume that it's just like a have the thickness paper.
But you said that the line, the second regime, the line is parallel to the axle, which means that
Yes.
it will provide the same load
Yes.
when the peak increase.
Yes.
Then why will the million peaks affect? Because it's just a lot of peaks.
I draw on the blackboard. So when the width is fixed,
Yes.
so if there is many peaks,
Yes.
you can assume it that just like have a thickness paper, a single paper, but it have the thickness.
Yes. But you just said that it will provide the same when a piece increase, it will provide the same load.
Yes, because it's like just like a thickness paper. So a same papers have the same loads.
I mean the load is that when you press it, the maximum load that you show here.
Yes.
So, and you said that it is like a paper which is much thicker, and you said that when a much thicker paper will not provide the same load.
I guess you know. But when the piece for example is the 6,
Yes.
and the minute, right?
Yes.
But we can maybe we can calculate the inertia of this piece and compare to this piece.
So actually, the line will decrease. Yes, the line is a decreased line.
I don't think so.
Then, I still can't get your explanation because you said that the line is not decreased
Yes.
when the peak was added. Then how do you think that when we put it? So there's another order which will make the line decrease.
You mean?
I said that you said in this graph the peaks will not the line will not this line will not decrease.
Yes.
Then if so when we provide a lot of peaks, it is still a line.
Yes.
Then it is like it didn't you have two explanations to us only at the same graph.
Two explanation.
Yeah, because you said that if the peak was increased to like 1 million or 1 billion, it's like a thick paper.
Yes.
And you said that the thick paper will not provide as much force.
I didn't say the singular won't provide as much force.
So you said that if we have a million volt, it will still provide the same force.
This is just my guess, but I think so.
Okay. Okay. And here, can you turn to your optimize about the sedative? And you said that there is 2 row, 2 rounds will be yes, you said the 2 rounds and 2 circles, which is a double cylinder, will provide a maximum payload. And can you explain? Because I didn't get your theory in this part. Okay, and thanks to the reporter for giving me such a great discussion. And I have a clear view of how he do experiment in his theory. And by here I know that his suggestion we suggest that he try to conduct this experiment to pull much more steady example of a machine but not by hand, which will make the experiment more accurate. And he has said that we have discussed about the different buckling between a long column and a short column, and which he didn't take into consideration, and which have different formula of the payload. And when there are million peaks, that the reporter thinks that it will also have the strength as the 7 peak did. And like I assume that the reporter had first give us the experiment, but he can't ensure that there are other shapes which can provide more load than 5.83 newtons, because he still didn't give us a much more clear theoretical explanation about this situation. And thank you.
3 minutes for the reviewer to ask questions.
Okay, first for the reporter, may I ask, how did you conduct your experiment on faults? Do you control the length of the column? So you cut A4 paper in pieces? Yes, the faults.
Okay. If the paper is the power of 2.
Okay, let me explain my question more. If this is the 4 volts, right?
Yes.
And how can you do your 2 volts?
You mean 2 volts?
Yes. Did you cut it in half or you use that?
No, I use that too.
And if you use this, wouldn't the column, the length of the column affects your experiments?
You mean the length?
Yeah, your length.
Okay, so
Yes or no?
you mean the length?
Yeah, the length. Would it influence your experiments too?
Yes.
Okay, thank you. And about the opponent, what is your opinion on the page number 17 about the faults? You have a million faults.
And the reporter sent me 17. I think that actually it's a decreased line because if you fold like
So it will decrease.
Yes.
Okay, thank you. And for both of you, have you ever considered other shapes apart from accordion style and the tube, the cylinder?
Yes.
Yes.
For example, name a few. Just name a few.
Like this.
The flat one. Okay.
But the strength is very, very small.
Okay. And how about you? Do you think that other shape might influence, like square, like pentagon, hexagon?
Yeah, just like the reviewer has said, the pentagon, hexagon, and other shapes might influence
Okay.
the.
Thank you. I got your points. And for the reporter, in your buckling theory, there's I think a constant.
Yes.
And do you know what is in the constant?
You mean
The meaning of the constant?
you mean the buckling the
Yeah.
constant? Okay. So this is the buckling. This is the max force
Yeah.
and equal to this is the formula, right?
Yeah.
And
And
we
you
don't-
simplify the formula.
Yes, I simplify this formula because this is
The constant, yeah.
6.
So, yes. Okay. And okay. Thank you.
Next. 2 minutes for the reviewer to make the preparation. Okay, 4 minutes for the reviewer to take the floor.
Okay. Good morning, everyone. I'm the reviewer from Team Excel. And first, I want to thank the reporter for a nice presentation and a fascinating discussion between the opponents. And first, let's do a little recap of our problem here. The question states that it's more difficult to bend a paper sheet if it is folded accordion style or in the tube. Use a single A4 sheet and a small amount of glue if required. Construct a bridge spanning a gap over 280 millimeters. Introduce parameters to describe the strength of the bridge and optimize some or all of them. And in the reporter's report, he had stated that there was the theory was that the bending moments and the buckling will affect whether or not the bridge will collapse. And this informs a static equilibrium. In his parameters, he had data on the shape and the folds. And I have some suggestion and appreciation for the reporter. First, he had a very organized data, a convincing theory that can prove his data was correct. And he had controlled some of the variables that only one of them changed. And an in-depth discussion between the variables and its results. But however, in some of his theories, there was too many words, and we cannot concentrate on looking at the words and thinking about theory. As for the opponents, he appreciates the reporter's experiments and he also questioned the validity of the data and mentioned some other parameters. But I think you can make the reporter some more time to think about his answers. And you spent too much time on the same question. And as the summary of the discussion, they had on the experiments, the theory, and the cylinder things. And I think the reporter has answered his question based on all his theories. And if I have some suggestions for the reporter, in the theory, should friction be considered as an aspect in the results? And is the paper you have a 3D or 2D models that will affect your theory? And as parameters, you can use different shapes, different angles of the accordion style, and that was actually wrong. And the last one was the glue. If you apply glue, will it affects the whole results? And overall, I think the opponent had asked some very in-depth question to the reporter, and the reporter has explained some of the theories clearly. And I think that was all of my review. Thank you.
Okay, we'll have 2 minutes for the reporter.
Okay, first of all, for the 2D and the 3D questions, what I read on the paper is that when the bending is on the, for example, it's on the on one axis, then we just consider the cross section. Okay, and then we did have do the glue experiment on the further PPT, and we get out if there's a glue in the paper layer, the strength will increase by just a little. It is due to the second moment of inertia, because the width is increased, so the strength increased too. And I want to say one more time about the buckling formula. And we know that the pi square is a constant, and in the same paper, the elasticity of modulus is a constant too. And the k is also a constant. It is a property of the end part of the paper. And the length is the initial length of the paper. So all of this is a constant. So the F will equal to a constant, multiply the I. So that's why it can. And that's all for my concluding remarks. Thank you.
We are open for the jury to ask questions. All silent. Emily? Yes.
So I would like to learn about the experience from the opponent and the reviewer. So according to your experiment, so how do you optimize the system to produce the maximum strength of the bridge? Okay. Just a quick answer.
I think that we should increase the thickness of the paper by folding it together, then fold it into a accordion style. How about the viewer?
In my opinion, that's if we use a thicker paper, that will change the modulus of elasticity in order to make the withstanding force greater. And also, if you apply glue on both sides, it will increase friction and makes the bridge from collapsing that easier.
Thank you.
Okay, Professor Wu.
Questions. First one is how many bridges have you actually made in reality to the second question is how do you think is the role of the group? What kind of a role the group can play in answering the question? Because the group is not discussed among the group.
So I answer first.
Okay, I want to hear the answer for the reports are.
Okay. So the first question is how many bridge do I?
Yeah, how many bridges in part-time? Because the question in the problem actually mentioned only 2 times.
Yes.
We don't without 2, so it's total 4 sometimes.
Yes.
How many roughly?
We did the experiment 5 of each, and the total is about 60s to 70s. The role of the group. Yes, we can get a clear picture from the vessel. So if this is if we fold the paper together and we put the glue in this part, the B will increase. And so the second moment of inertia is equal to BH cubed over 12. So when the B is increased, the I will increase too. And the force is have relationship with I. And when the I increase, the force will increase too.
And first, am I allowed to talk about my experiment?
Just
Okay, and in my experiment, I have did about 90 bridge total and about 6 to 7 for each paper bridge, each condition. And I think that the role of the glue is because if you stick the glue to a bridge, it will affect the end condition of the bridge, will affect the K written by the reporter's formula. So it will be different affecting, I think it's mainly the role of the glue. Thank you.
Okay. In my experiments, I did the 25 data for each parameters, like each group. So we end up like folding around 900 to 1,000 pieces of paper in the total experiments. And I think the glue has 2 parts in the.
among the 1,000, how many of them use glue?
For only a few, just the last parts, like 200 or so. And I think the glue had 2 parts in the results. The first one, it increased the friction among the table, so it can withstand more force from falling down in the gap. And the second part, it increased the strength of the paper, just as the reporter said, but in a different way. We increase the strength, making it harder to bend.
Well, I think that's about all the time we have. Okay, now we'll show the reporters' scores. 7, 8, 7, 7, 7, 7, 7, 8, 7, 8, 8. Next, for the opponents. 6, 8, 8, 8, 8, 8, 8, 9, 8, 7, 7. And finally, for the reviewer. 8, 8, 7, 9, 9, 8, 7, 7, 8, 8, 8. Okay. 10 minutes break. And please, the participants